Good morning, everybody, and welcome to week 6 of Physics 3. As we discussed last time, today is going to be basically, we'll try to finish relativity today. Relativity is a big topic. Even the special theory of relativity is a big topic by itself. And we're going to do it in somewhat of a truncated way, and I will explain what I mean by that. And then if we can't finish it, we're going to finish it Tuesday of next week. There will be no class this Thursday because there will be an exam. Basically, the exam is going to be open from 8 o'clock in the morning until 1 p.m. You will have 2.5 hours to do the exam, and that includes the upload and everything else. So you will have about 2 hours to do the exam and about half an hour to figure out your way of getting the exam basically uploaded to Canvas. And which means that since the exam is open at 8 o'clock and ends at 1 p.m. in the afternoon, you really cannot start the exam after 10:30 if you want to give yourself the 2.5 hours to complete the exam. So you have anywhere between 8 o'clock in the morning until 10:30 to take the exam, to start it actually, to take full advantage of the 2.5 hours, because at 1 p.m. the exam ends. So that's basically how, as far as the exam. The exam again covers chapter 17 through chapter 20, the 4 chapters from the beginning. Chapter 37 is part of exam 2, which is not today. We are in week 6, which put us exactly 1/3 of the way on into the course. So we're in pace to finish the course on time. If you think we're going too fast, please let me know. If we think that you need to have more examples, let me know. In this chapter, I think I have about 5 or 6 problems, but I'm not going to do them until after the exam, which means next time when we meet, which is Tuesday. So basically, this is as far as this one. And the lab is, again, we're going to go briefly on it next Thursday when we meet. But again, this is for chapter 37 and beyond, chapter 38, and so on and so forth. So this is where we stand. Any questions before we continue the topic of chapter 37? Questions related to the exam, okay? No questions, no problem. Then let me share with you the screen. So this is where we left off last time, basically, where we thought that we need to build some stuff. As a matter of fact, there is more to it than this one. Of course, there is the simultaneity, meaning that if two events are simultaneous in one reference frame, they will not be in another inertial frame that is moving with respect to another one. So that is critical for the lab. And also time dilation and length contraction. Both of them are also going to be experiencing changes. In other words, the person who is moving, the person in the moving frame will accuse me, the one who is stationary, of having the wrong clock, because his clock will tick seconds, my clock will tick slower. That's what time dilation means. I accuse him, though, of having the wrong ruler, because I look at his ruler and I think it shrunk in size because he's overestimating the distances. So now we have kind of a dilemma in here, how we can resolve these things. These two are exactly what needs to be done so that the speed of light will remain both the same, okay, for both observers, okay? So this is the issue with the time dilation and length contraction. In addition, as one of the consequences of the time contraction is we have to go and review a Doppler effect that you guys did in physics 2 and see how that needs to be corrected when the object is moving with high speeds. This is true, especially for neutron stars and supermassive stars that are orbiting one another. They can move with extreme high velocities, that their Doppler effect is no longer classical. In a sense, we have to treat it with the relativistic corrections. So all of that is part of these things. There is another element in here that is a problem. In classical mechanics, anything can cause anything else because there is no speed limit of information. So meaning there is the causality in that case is always respected. In other words, your grandfather is responsible for you being born at some point, okay? So this is there is a cause and there is an effect. In classical mechanics, this is always true, no matter what. In relativity, because of the way that we measure time, there is a problem. Is causality going to be broken? One of the fundamental laws of nature is causality should be respected. In other words, you should not be able to travel back in time and basically cause the end of your grandfather, in other words, which causes the end of yourself at the end. So there is a problem. There is a breakdown in here of causality. So we need to find a solution for this problem. There is another thing also, that the experiment of I'm sorry, guys, I'm having technical difficulty in here. I'm trying to resolve them. Okay, hold on. Can you guys see my screen?
Yes.
Yeah, we can.
Okay, very good. So we're going to resume without camera. I'm sorry about the camera. I don't know what happened to it. I will check it later on. Anyway, is the sound coming clear or not?
Yeah, it's perfectly clear.
Okay, very good. Thank you. Again, I don't know whether we get disconnected, but the point I was trying to make in here is that there are some the issue of the causality, which is something of importance in relativity. In other words, we have to address it also. It's not a problem in classical mechanics because time is absolute. Okay. However, in this case, because time changes, we really have to make sure that if an event can cause another event, then that also stays for both frames, whether the moving frame or the stationary frame. And also another issue that we need to address, and that is how the velocities add. We have to make sure that the experiment of Michelson and Morley is actually can be reproduced by this theory. The last thing that as I was talking about is the Doppler effect. The Doppler effect also needs to be corrected, because when we did the Doppler effect in physics 2, that has a term in it where the frequency that is perceived is different than the actual frequency that is sent. But we will see that time is no longer measured with the same units. So the time is related to the frequency. The inverse of the period is the frequency. So that needs to be also corrected. And then at the end, we're going to finish with the energetics, basically the dynamics here, and the energy, okay? Energy balance. So this is some sort of like dynamics, like when you did F equals to ma, with the exception that we're going to do it in some sort of an awkward fashion, and we'll try to explain it. And we're going to get to the correct answer, okay? This is the famous E equal to mc square result. So we'll try to do all of that. Hopefully we'll finish it. If not, then we'll probably have to do it some other time to finish it some other time. Okay, the first thing is the simultaneity. Simultaneity. In other words, assume that there are two events recorded by coordinates x1. We're taking just the time, the one coordinate. Basically, the y and the z are the same for both reference frames, because we're assuming that somehow we're moving parallel to both of them. So we're only moving in the x direction, that's all. So the x is shifted to the new x prime by ut, with the vantage point of this one by ut prime, okay? With the other one is going to be actually negative ut in the opposite direction, okay? Because if you're sitting in here, you see the other reference frame moving in the opposite direction with the velocity u. So having said that, so the time now is changing too, where we found that relationship. So we have an event x1 at t1, and we have another event at position t2, at position x2, with a time t2, but we're requiring that time t1 and t2 be the same. This is what I mean, that two events, this is event 1, and this is event 2, they're taking place in the same time. That means their times are the same. The difference in time between them is 0. That means what I mean by being simultaneous, as far as I'm concerned. I know that they happened in the same time. That's exactly what that means. So when we did the coordinate transformations, we found that x prime from the vantage point of the moving frame is going to be given by gamma times 1 minus, because it's moving in the opposite direction, so it's going to be a plus actually. Sorry, 1 x, sorry, plus ut. okay? I'm sorry, it's minus. I'm always overthinking this minus sign in here. Okay, let me okay, so you are in the moving frame, you're measuring x primes, okay? So from your vantage point, your x prime, which is just this distance, and this is x, the whole distance, and this is u, but it's moving in the opposite direction. So from the vantage point of the original observer, here is how the relationship looks like. So from my vantage point, x is equal to x prime plus, this is x prime, plus ut prime times gamma. Yes, that's correct. And from my vantage point, x prime, from the vantage point of the moving frame, x prime will just be gamma times x minus ut, okay? Hopefully that explains it. Just look at the geometry in here, it should be fine. So again, it's gonna be x minus ut, okay? So this is the vantage point of the moving frame. So t prime is going to be gamma times t minus, again, u over c squared times x. Now,
Professor, can you remind us what u represents?
u represents the velocity of the moving frame. So here is O prime, and here is O, observer O. Both of these frames, so this guy records positions with a prime in them, t prime, and this one records position without the prime in them. So this is the person sitting on the station, and this is the person sitting on the train. Okay, the train is moving with the velocity u. Make sense now?
Yes.
Okay, so for the person sitting on the train, he or she records positions from the point O prime at x prime. This person records this position, the same position at position x. Obviously, from the geometry in here, x is equal to u times the time that this person is recording, plus x prime, and with the factor gamma. The fudge factor gamma was needed really to make sure that the velocity of light is the same for both observers. So that's how gamma came in. Gamma turned out to be that 1 over square root of 1 minus u squared over c squared. Okay, this is what needs to happen for us so that both of them will measure the same speed of light. And that's how we derived that result. Okay, so here is the question. If these two events in this frame, from the calculation of this frame, happen in the same time, they will not happen in the same time for the other frame, because delta t prime, as you can clearly see from this equation, which I'm going to label 2 in this equation 1, from equation 2, immediately I'll find that delta t prime is equal to gamma times delta t minus u over c squared times delta x. Obviously, delta t is 0, because those two events happen in the same time. One of them at x1, the other one at x2, but both of them happen in the same time. This is the separation between the two events. That's delta x. That is x2 minus x1, okay? Obviously, delta t prime is not equal to 0. It's equal to minus gamma times u over c squared times delta x. So this is not 0. So which means that the two events that happen to be from the vantage point of the person in the station in the same time, for the person who's moving, they're not in the same time. They happen at two different instances. As a matter of fact, I can calculate T2 prime minus T1 prime is a negative number if x2 is, of course, greater than x1. Here is how it looks like. Let's say, for example, we are here. Here is a train. And I'm looking at it. It doesn't matter what I look at it. I'm looking at it in here. So this is observer O. This observer, we're going to put him right, for example, smack in the middle. This is observer O prime. This is the front of the train. This is the back of the train. Okay. And let's say in the same time, lightning struck the both ends of the train. So this is the front end of the train. This is the back end of the train. They were hit by lightning in the same time. For me, this two events, which is lightning striking the front of the train and lightning striking the back of the train, happen in the same time, where delta t is equal to 0. But this person is moving with a velocity u, and the light coming to him from this front end is moving with the velocity c, and the light coming to him from the other end is also moving with the light c. But he's rushing to meet the front end. So he will see the first light from the front end first. This is x2. And then later on, because he's moving away with the velocity u from this one, later on, when the light from the back will catch up with him. So he will see that this event took first place, the front one took first, and then later on. So T2 prime is recorded first for him, and then later on T1 prime. You guys understand now how his perception of time has shifted in such a way? The same event from the vantage point of the observer outside, which happened in the same time, their delta t is 0. Their delta t is no longer 0. Actually, the front one happens first, and then later on the second one in the back happens later. Make sense?
Yes.
Okay. So this is basically what we mean by simultaneity being broken, meaning two events that happen in the same time in one reference frame do not necessarily mean that they will happen in the same time for another observer. Okay, so this is item 1 of discussion. You're going to put it in your own words. What happened to simultaneity? Simultaneous events for one observer are not necessarily the same for the second observer. Okay. The second issue is time dilation. Okay. Imagine with me for a second that we have observer O prime sitting in the same point recording the ticks and the talks, the ticking of the clock. Obviously, the clock is sitting in one point and it's ticking time. It's going from 1 to whatever it is and then back. So it's an event that keeps on track of time. So there is a tick and a tock of the clock. Okay. So it goes like back and forth, back and forth. I know I don't have my camera, so I'm trying to mimic the pendulum. So the pendulum, when it goes in the front and comes back, that is, let's say, for example, 1 second passed. Okay. So this is what I mean by the ticking of the clock, ticking of the time. So this for him is what is known as a proper time. So for you, for example, it could be your aging. Every second you age a second. Every 2 seconds you age 2 seconds. Every hour you age an hour. Every year you age a year. So let's say, for example, what I mean by the proper time is that every birthday celebration, okay, from birthday to birthday, that is, if you wish, your tick and tock. That is basically your clock ticking. That is basically your biology doing whatever it does. So that's your proper time. Okay. So this is observer O prime. Observer O, on the other hand, sees you moving with the velocity u. Okay. Or actually, because you are not moving, then in this case, we can just refer to u as being v. Okay. Simply v. Okay. So now what happened to time from my vantage point? So this is time. This is t prime. But in here, it's happening in the same place. So delta x is equal to 0. Okay. The clock is not moving in your frame. Delta x prime, I should say. Delta x prime is equal to 0 from your vantage point. The clock is sitting in your place. And even you, for example, you can sit for the entire year in your place and you're going to celebrate your birthday next year. Does this make sense to you guys? That this is your proper time?
Yes.
Yeah, that means that even if you don't move, okay, you're sitting on a chair for an entire year or for an entire hour or for an entire 30 seconds, it doesn't matter how long it takes, you have aged that much. That is your event. That is what I mean by your proper time, t prime. So actually it has a name, proper time, they call it tau. Okay, this is a fundamental property. This is, you only know about it. It doesn't matter what everybody else is moving, you have that clock. Nobody can deny you that right. This is your intrinsic right. This is your right. This is, if you wish, your God-given right. Okay, your proper time is unquestionable. However, when I'm looking at it from my vantage point, I'm measuring different times for you. This is the time I'm measuring for you that has lapsed during the tick and the talk. It's delta t equals to, again, gamma times your delta t prime, which is, I'm calling it tau now, plus the corrections coming from space, which is equal to, what is it? So I have to add the other one because I'm using my vantage point. So it's going to be a plus now instead of a minus in this expression. So it's going to be plus your velocity, which is v now, over c squared times delta x prime. But you're not moving, so this is 0 anyway. I mean, the clock is ticking in the same place, so that's 0 anyway. So it doesn't matter for the plus or the minus. So the way I measure the lapse of time, delta t now, is equal to gamma times tau. So if 1 second has lapsed, gamma, by the way, is equal to 1 over square root of 1 minus v squared, or v squared in this case, over c squared. Okay? This factor is less than 1. This factor is less than v is always going to be less than c. So which means that gamma is going to be actually more than 1. Let me show you another. Let me stop sharing this screen in here, stop share. And let me share with you another screen about how gamma depends on everything else. Share. What is the share button? Because it's important to have an intuition of what this gamma is. Okay, what I have in here, I have defined the gamma function of beta, okay, where exactly beta is equal to v over c, okay? It's the ratio, basically, of the velocity expressed in terms of c. If you can clearly see, here is a definition of the function itself. Again, I mean, I wrote it in here in 1 over square root of 1 minus beta squared. Does that make sense to you guys? That v over c is beta, and actually that's how we call it always. Even in lecture, we call it beta, which is the ratio of the velocity with respect to the velocity of light, speed of light. Okay. So this is the function. So I'm trying to plot the function gamma in the range between 0 and 1. Basically, that's because after that, if beta is more than 1, this becomes imaginary, because this square root of a negative number becomes complex, and we don't know what that is. There is no, I mean, we're dealing with real numbers in here. So this is the function gamma. This is the gamma factor, basically. And so if you go to look at this plot in here, and I'm doing some exclusions in here again, because the denominator will vanish at this point. And I'm drawing these 2 lines. Okay, here is the point. From this graph, gamma is always more than 1, no matter what. In classical physics, when beta is very close from 1, meaning, I mean, very close from 0, meaning that v is very, very small compared to c. That means beta is practically 0. That means I have 1 over square root of 1, which is 1. So the minimum value I can have for gamma is 1, and that is for classical physics. Classical physics, where you are very, very less than the speed of light. 1 is exactly at the speed of light. Okay. 0.2, it's still a huge speed. 0.2 times 300 million meters per second is 60 million meters per second. So as long as you're moving slow, which is typical speeds, you are very much in this range. Gamma is 1. Once velocity starts to increase and you are at 80% the speed of light, then gamma is appreciably more than 1, and it's still less than 2. When gamma is like 90% the speed of light, you're looking at something like 2.5. Gamma is greater and greater than 1 more. But when you approach the speed of light, obviously this becomes an asymptotic behavior, and gamma becomes bigger and bigger. At this point in here, we are at probably 98 or 97%. Gamma is 5. But it's going to increase to infinity if you reach, because of this behavior. Does this make sense? Does this graph make sense to you guys?
Yep.
Yes, no, maybe?
Makes
Yeah,
sense.
makes sense.
Yeah, this is basically what I'm looking at in here. Gamma is always more than 1. That's the, in classical physics, it's equal to 1. In classical physics, classical mechanics, I should say, when v is over c is very much less than 1, that means v squared over c squared is very, very much less than 1, then I can neglect it and gamma becomes equal to 1. Otherwise, gamma is always greater than 1. So that's the point in here. What I'm trying to say in here is, if 1 second has lapsed in your time and gamma is more than 1, then more than 1 second has lapsed for me. More than 1 second. Because of the fact that gamma is more than 1. Does this make sense? That means that, let's say, for example, you're moving with almost the speed of light, okay? Then you age less than the way I measure it. Here is what that means, okay? Take two twins at the age of 20. Twins, they have the same age. One of them decides to travel with almost the speed of light, okay, to a far away star. Let's say, for example, Proxima Centauri, which is about 4 point something light years, okay, and comes back. So if he goes and comes back, and let's say it's almost the speed of light, 99.9% the speed of light, his age when he returns will be about 21 years old. His brother, who's sitting in here, this is when he returns, of course, they will meet again. So when he comes back, so he goes to Proxima, here is Proxima, and comes back. For him, he's at the age of 21 years old. The one who stayed in here, when they meet in here, Proxima is about 4.2 light years. So he's going to be about 28 to 29 years old. So you have two twins at the same age. One of them travels with almost the speed of light, reaches Proxima here, and comes back. When he meets with his brother, there is a gap in age, because this clock in here, his internal clock in here, ticks the normal way. This one's clock, the way he perceives time, looks at his twin brother and thinks that his clock is ticking slower, okay? Because he will age faster, because delta t in here will be bigger than this proper time. So this is the problem of the twins. Okay. You might ask, and it's a very legitimate question, it's just that these twins, one of them decided to travel to Proxima and the other one stays on here on Earth and came back. Isn't it possible, from the vantage point of this brother, is that from the vantage point of the traveling brother, he sees his brother traveling away from him with a velocity that is almost the speed of light. Wouldn't he assess that this brother is the one who's going to age less because of his clock being slower? Well, the problem is this one, in order for him to accelerate to that speed and slow down back to the speed of time, there is an asymmetry in here. You cannot make this argument, in other words, okay? So in other words, truly, the brother who stayed in here, the non-accelerated brother, will really age higher than the brother who traveled. So this is an issue with the time delay. The point being in here is, this is the expression that gives you the time dilation. The proper time is multiplied by a factor of gamma in order to find the time as measured from the non-moving frame, okay? Make sense? Yes, everybody? Or am I going too slow, too fast now?
No, I got it. I'm just writing it down.
Yeah, makes sense.
Okay, very good. Here is the second item of the discussion, item 2. Time dilation. You need to put it in your own words. Okay, if you want to give the example of the twins, that's fine. Here is another problem now. Let's say, for example, this is again observer O prime moving, everything is primed in his frame. This is observer O stationary, where everything is unprimed in his frame. He looks at the ruler that this guy has. Here is the ruler, okay? The ruler, obviously, for this guy is L prime. And he wants to measure that ruler, how long it is. So observer O wants to measure this ruler, how long it's going to be. This is 1 meter, for example, if you like, okay? This is a meter stick. He wants to know how long is the meter stick that this one claims to be a meter stick. So this is what he does, okay? He comes to this end and measure its length, which is x2. And he comes to this end and measure its length, which is x1. Obviously, he has to do both of them in the same time. You cannot measure a ruler by looking at its front end and wait a year later and measure its second end because the ruler might move. So you really have to do, that's what you do when you measure rulers actually in the lab. You have to measure both ends in the same time. When you measure how long is the desk, you cannot measure the desk now and wait a second later and measure its desk because the desk might move. So that's the point in here. So in other words, this is a simultaneous measurements of both ends of this ruler from the vantage point of observer O. Obviously, I need to look at the expression that he's using in here. X1, or let's take X and then we'll take the deltas. It's the same thing. It's going to be, again, gamma times X prime plus UT prime. That's his measurements of length. And T, obviously, is given by gamma times T plus U over C squared times X primes. So these are primes in here. He's taking the data of whatever this person is using. What I said by X, this is X, okay? That he's going to measure. When I said X2, this is X2, T2. And he's looking at his watch, and this is the recorded times. It has to be the same time. So from this requirement that the delta T for his measurements be 0, that means that he concludes that delta T prime is equal to minus U over C squared delta X prime. This is his conclusion. Okay, because he's unaware of what the other one is. The only thing that he knows is that this length is L prime, which is 1 meter as far as this guy is concerned. Okay, he wants to check if it's really a meter or more or less or how much it's going to be. So he takes this expression and he plugs it into the length that he's going to measure. Obviously, he's going to measure the length delta X is equal to gamma times delta X prime plus U times delta T prime. All I did was apply the deltas to this expression. Okay. So, and in here, I require that this delta is equal to 0. Obviously, gamma is a factor that doesn't depend on the this measurement. So it's going to be delta T prime plus U over C squared times delta X prime. This has to be 0 for him to do the measurements. So this quantity has to be 0. That's how I concluded that this is actually equal to 0. Anyway, I mean, they are equal to one another. So anyway, now he's going to plug in the measurements for delta X and finds that the delta X, the length that he measures for that ruler, is going to be gamma times delta X prime minus, because I have a minus sign in here, U times U is U squared over C squared times delta X prime. And delta X prime is that ruler in the moving frame. That's L prime. So he looks at it and says that the ruler's length is gamma times 1 minus U squared over C squared times L prime. However, remember that gamma squared is equal to 1 over 1 minus U squared over C squared. That means that 1 minus U squared over C squared is actually 1 over gamma squared. So the way he measures length then, L is gamma divided by gamma squared times L prime, cancel one of the gammas, and this becomes L prime over gamma. So the length has shrunk by a factor of gamma. Remember, gamma is more than 1? So the length has shrunk by the factor gamma, whereas the time has extended by the factor of gamma. Where is it? Gamma tau. And the length, so in other words, he sees the ruler and he thinks the ruler is not 1 meter, but it's less than 1 meter. So imagine gamma is equal to 5. If gamma is equal to 5, that means the time for his vantage point is equal to 5 tau, and the length L is equal to whatever L prime, in this case I called it L prime, divided by 5. So basically, the length has shrunk by a factor of gamma. So this is what we call length contraction. Okay. You guys guess what the third item of discussion today is? Anybody? Anyone? What this item is going to be? I don't have my camera. I'm sorry. I need to. What do you guys think this item of discussion is going to be? The third one. The first one was dealt with the simultaneity. The second one with the time dilation, and the third one is going to be. Any suggestions? Somebody chatted. Okay, the second one was the time expansion or time dilation. The third one, I'm suggesting, what do you guys think is going to be? Make sense? It's about the length contraction. Sounds good?
Okay. Yeah, sounds good.
Okay, so that's the third item. So you guys know where we're headed now. How do we know all of this is if it's true, if it's really what we're saying in here, okay? Because here is the thing. There is a problem in here. This guy, because it's proper time, he accuses the other one that his clock is ticking too slow. I mean, he's accused of having a clock that ticks too slow. So he's accusing the other one that he's accusing that his clock is going too fast, actually. Okay, because I am aging normally. I only went 1 year. How could you measure it for years? So your clock must be going too fast. Okay, this one actually there is a backward discussion in here. This one is accusing the moving frame that he's using a short meter stick. So it's not a full meter. It's 50 centimeters or 20 centimeters, depending on the factor gamma. The other one accuses him again of using a long meter stick. So that both of them at the end of the day will find the same speed of light, because these two factors will cancel. No matter what gamma is, at the end, they will both find the same speed of light. So that is really the essence of where this discrepancy is coming from, the length contraction and the time dilation, okay? So these are the two. How do we know that? Let me give you an example, which is really a problem that came way after these things, the mu1, okay? The mu1 is known to have its own time. If you do a lab, for example, in a nuclear accelerator, and a mu1 is created, and you do all of the experiments and repeated time and time again, you will find that the mu1's life can never exceed 2.2 microseconds before it decays. So mu1 decays into something else after 2.2 times 10 to the negative 6 meter per second. I'm sorry, seconds. What am I talking about? Okay, so this is its lifetime. This is basically how long it's going to live. So this is its tau, life. That's it for the mu1. So here is the problem. Mu1s are created in the upper atmosphere. The atmosphere. And they travel all the way to the ground. We detect them actually on Earth. Okay, we find them on Earth. And the distance between the ground, where they detect where the thick atmosphere is, and the ground is about 10 kilometers. So how come mu1 that can live at most 2.2 microseconds can travel all the way for 10 kilometers and be detected on the ground? Let me explain what that is. If the mu1 is traveling with the speed of light, which it cannot because it has a finite mass, okay? It's mass of particle. So if its speed is equal to c, okay, this is the fastest it can go. It cannot go faster than this. The distance it's going to travel, if we do speed times time, which is c times tau, is going to be 2.2 microseconds times the speed of light, which is 3 times 10 to the power 8 meter per second, 300 million meter per second. And this is second, cancel the second and second. So the most it's going to travel is 3 times 2.2, which is 6.6 times 10 to the power 2 meters, or 660 meters, less than a kilometer. And then it should decay. Even if it travels with the fastest speed on Earth, on the universe, which is speed c, the maximum it should travel is 1 kilometer, less than 1 kilometer actually, 660 meters. That's it. It cannot travel faster than that. I mean, more than that. It should not be detected on ground. Yet in nuclear accelerator, I mean, in labs everywhere, including Fermi Lab in Chicago, we detect them all the time on the ground. So how can we explain that? Let me explain it from 2 points, okay? From the vantage points of the lab, and then from the vantage points of the mu1, somebody sitting on the mu1 and traveling. Okay, here is from the lab. From the lab, we measure delta t, and delta t is equal to gamma times 6.6 times 10 to the negative 6 seconds. So gamma can be very large if it's traveling even very close from C, not necessarily C, okay? Can be, for example, 10, okay? Or 100. If it's 100, that's enough factor to bring this to 6.6. If it's 10 only, if gamma is 10, okay, it can change tau enough so that we multiply its speed by the time enough so that the distance traveled is not 660 meters, but about 7 kilometers. If it's more than 10, let's say, for example, 12, then in this case, it's enough for it to reach the ground and even in the ground, okay? So depending on the value of gamma, which is again equal to 1 over square root of 1 minus beta squared, okay? This number can reach any numbers you want. I showed you the graph before, and it can be 12, it can be 15, it can be 20. So the time from our vantage point did not live just for 2.2 meters per second. It lived more than that by a factor of gamma. Well, from the vantage point of the mu1, there is no time difference. It only lived tau. That's all. That's all it lived, 2.2 microseconds. So what does it see in this case? It sees the entire 10 kilometers shrunk to less than 660 meters by a factor of gamma. So it sees the distance it travels, d, as being the 10 kilometers divided by the factor of gamma. So the 100 or the 10 kilometers, let's say, for example, we divide it by 12, it's going to be enough, or probably 15, it's going to be enough for it to be less than 660 meters. So let me divide 10 kilometers divided by 15. It's not giving me that. I need the calculation. Where is the calculation? Anybody doing calculations in here quickly? What is 10 divided by 15? Yeah, it's actually, we need more than that, 16. In other words, there is a gamma that will make it happen, okay? With 16, the distance will shrink to be 625 meters, okay? And that's enough for it to live long enough to travel that distance of that it needs to travel before it expires, before its life goes, before it decays, basically, okay? You guys understand this example or not? This is actually a real problem. This is a real example, not a hypothetical problem. The life of the mu1 and how it decays. So from the vantage point of the lab, it says that its time is not actually 2.2 microseconds, but it's factor of gamma. Why did I put 2.6? It's 2.2, okay? By factor of gamma. So it lived long enough, 16 times, for example, if I take gamma large enough, I can find that delta t is long enough for it to travel the entire 10 kilometers and some, okay? From the vantage point of the mu1, it did not live longer than 2.2 microseconds. It lived exactly 2.2 microseconds before it decayed. Then it sees the distance it travels shrunk by the factor of gamma. So instead of traveling 10 kilometers, it travels less than 660 meters. So it's going to travel something 600 meters, for example, it's moving too fast, or 650 meters is moving slower, but still very fast. Does this make sense to you guys?
Yeah.
Okay, so this I had a chance, both me and my students, when I was actually in the Midwest, to go to Fermilab and see actually what they are doing there. They're actually more concerned with the neutrino nowadays, because it's a big problem trying to understand, for example, the dark matter and all kinds of other problems. But the mu1 is actually a side thing that they did a long time ago, and other people did a long time ago, but it's a detector everywhere. So this is an example of why link contraction and time dilations are actually something real. This is not, classical mechanics will never be able to explain it. If it were to classical mechanics, mu1 should never be detected on the ground. If classical mechanics is correct, mu1s should never exist on the ground, period, end of the story. They should never be detected on Earth. I mean, at least on the lab. So they could be detected. You have to send balloons up in the atmosphere to find them. That's it. But that's not true. We find them actually on the lab all the time. So the only way this is true then is if relativity is correct. So this is actually a strong confirmation of this theory. So it's not just something that came out of nothing, okay? Let me talk a little bit about causality, which is actually another element in here of importance. Okay, let's take event 1, which has coordinates x1 and t1. And let's take event 2, which has coordinates x2 and t2. Event 1 can cause event 2 if t2 is greater than t1. It doesn't mean that every event that happens before t2 can cause event t1, can cause it, but as a condition for event 1 to cause event 2 is that there is a delay in this way. In other words, event 1 must happen before event 2 to cause. This is a condition of causality. It's not. It's not. It's necessary, but not sufficient. Okay. So in other words, this must happen before the other one. That is basically the condition for the causality in here. For event 1 to cause event 2. We want to see if causality is violated, because it should not, okay? Causality is a big principle. Otherwise, we will have problems. I mean, like I was saying, you can cause, for example, the non-existence of yourself, which is a problem. You can go back in time, basically, and do something that could cause your parents not to exist, which cause you not to exist. Then how did you travel to begin with? Which is a problem, okay? So in order to resolve this one, here is the issue. So again, T prime is given by gamma times T minus, I always get this minus and plus. You have to really think hard about this thing in here of the different scenarios in here. So we're measuring T prime now. So it's going to be a minus, yes, U over C squared X, okay. Let's calculate the deltas, the changes in this times. Delta T prime is equal to gamma times delta T minus U over C squared delta X. What I'm saying in here is that delta T prime, what I mean by it is T2 prime minus T1 prime. The same two events as measured from the other observer, because this event 1 is recorded from the moving observer as being actually happening in location x1 prime and at time t1 prime, and this one is happening at x2 prime and t2 prime. It's the same events that cause each other, that one of them caused the other. But now it's from a moving frame perspective, he is recording different data for them, okay? Could still causality happen? Could still this condition of causality true? In other words, T2 prime, is it T2 prime greater than T1 prime? That's the question that we want to know. In other words, could event 1 still cause event 2? Okay, that's basically what we're trying to resolve in here. Here's the calculation. So that's the delta T2 prime. And what I said by delta T is actually T2 minus T1. Obviously, delta X is simply going to be X2 minus X1, the location of these two objects, which could be in the same location. It doesn't matter really. And the same thing with delta X prime is going to be X2 prime minus X1 prime. Obviously, if it were to cause it near it, then that's fine, okay? They have to have the same delta, delta X equal to 0 if it's in this frame. Here is the issue. For delta T prime, let's say, for example, causality has been violated. Assume causality violated. And we will see that this assumption is not going to work, okay? If it's violated, that means that delta T prime is negative. That means T2 prime happens before T1 prime. that means T2 prime is less than T1 prime. That will violate the condition of causality. Remember, it's a necessary condition to have T2 prime actually greater than T1 prime. But I'm saying in here that let's assume that it has been violated. Okay, let's assume that actually T1 prime does not happen before T2 prime. Okay, so if that's the case, that means this delta T prime is negative, which means that this whole thing is negative. That means delta T minus U over C squared delta X is actually negative, which means that delta T is less than U over C squared delta X, which means that if I move things around a little, that delta X over delta T is greater than, I moved this one to the other side, so the sign changes to the other side. So it's going to be C squared over U. That's all I did. I divided by delta T, and I flipped this fraction in here. So that's basically what this expression is saying. Well, that means that delta X over delta T is greater than C over U times C. That's what this expression is saying. Well, U is always less than C, which means that C over U is always greater than 1. If it's greater than 1, that this number is greater than 1 times C, so this number is greater than C anyway. And this is a violation. This cannot be. That means that somehow there is something that travels from x1 to x2 in the interval of time t1 and t2 greater than the speed of light. And that is a violation. This is a no-no. You cannot have something that travels faster than the speed of light, no matter what that is, even the information, okay? The information, the maximum travels with the speed of light. So in this case, this assumption is incorrect. So you cannot have a violation of causality. In other words, this condition is true. If T2 is greater than T1, that means that T2 prime is greater than T1 prime. Makes sense? Let me illustrate this one with another example in here, with another visual, actually. This is due to Minkowski. And this is important for your lab, by the way, Minkowski. Time is represented always on the y-axis, and the space is represented in the x-axis. The maximum you can travel is the speed of light. So this is the curve CT. You can travel backward also. I mean, in the negative, the x direction also. So you don't have to go forward. You can go backward also with the speed of light. So this is negative CT. Okay. Any thing, because you cannot travel faster than the speed of light. This is actually, if you move with a certain velocity, this is your path. Okay. Depending on how you want, you could have traveled back in x, you could have traveled forward in x. You can still actually go back in x if you want to, but as long as your velocity is less than the speed of light, this is the curve that you're going to go. This is your word line curve. Anything that happened in here is your absolute past. Anything that happened in here is your absolute future. In other words, future. Okay, U-T-U-E-R-E. Okay. Anything that happened in this side is also your absolute future. Anything that could happen, that happened in here, could never have caused you anything. Okay, it's outside of your cone. This is called the light cone. The reason why it's cone, actually, it's not just the shape, is because there is an Y and the Z direction also that I'm not drawing in here. And this cone in here is drawn actually in a 4D dimensional space. Okay, so this is a light cone. The entire shape that is by the blue light, by the blue lights in here. So anything in here that it happened in the past in here can cause anything of your own, because it can travel to you as long as it travels with any speed less than the speed of light. So you could blame anybody in here for whatever happens to you here. okay? But anything that is in this region has a solid alibi. If something happened to you in here, you cannot blame them for anything in here. This is outside of your cone, outside of your causality region. It cannot cause you anything, okay, harm or good or anything like that. Same thing. This, you cannot cause them any harm. Anybody in this region is outside of your zone of influence. Anybody in here, you could potentially do anything you would want to from this point on. You guys understand this? So this is basically the Minkowski representation of this whole thing, okay? Does this graphic make sense to you guys? Obviously, you're used to x in the opposite direction and t to the opposite direction, so you're used to drawing x as a function of t in such a way this way, but we're drawing actually vt. This is the going, usually you're drawing x equals to vt this way, but we're drawing t equals to x over v this way. V is less than the speed of light, so, and it can be 0 practically. So if you're sitting still, you're here, and you're moving in this line. You're not moving at all, okay? Because your slope then will be infinite, because 1 over 0 will become infinite, and this is the y-axis, okay? If you're moving slightly tilted with a small velocity, as it's small, this is going to have a higher slope on this side than CT. This is the maximum, or if you wish, the least slope that you're going to have in this representation, okay? So this is how it's presented in the Minkowski representation in here. So if you're sitting still and not moving at all, you can still move in this direction. If an object is moving with a velocity v, it's going to move in this direction, okay? So this is vt, where v is less than c. Obviously, if you take this one and flip it backward, you're going to see it the way that you represent usually x as a function of t. We're representing t as a function of x in this graphic. Make sense? Yes? Am I going too fast in here?
It makes sense.
My sound is really kind of I'm not hearing. I mean, the sound is gone too with the camera. So depending on that camera, but for some reason now sound is kind of weak. Does this make sense to you guys or not?
Yes.
Okay, very good. Very good. Thank you, Matthew. And I don't know who spoke because I can't see things now anymore. Anyway, so this is causality, which is a big deal when you do a relativity. There is another thing. I don't think that we're going to finish the topic now because we still have some other things in here, okay? Let me talk about the Doppler effect, which is actually essential for your lab, for your, not lab, for your homework problems, Doppler effect. When you did the Doppler effect, we're going to do it in the simplest case, okay, where we have the source moving. Because usually that's the one that we're interested in because we're sitting in the lab and started moving super fast or something, okay? So here is the source. Here is the observer, O. The source sends a wave. The wave reaches us now. So this is the wave front. I know you did this discussion in physics too. And the source moves now with the velocity u towards the observer in this case, okay? The source moves with the velocity u and then later on sends another wave. Ultimately, this wave will travel this distance now. It doesn't travel this whole distance, it travels just this distance. So for me, I record the time t that separates between two wave fronts because this is when the next wave front. So this is wave front number 2. This is the first wavefront. So the time, the delay between these two is what I measure t, okay? And they're separated by this distance, which is clearly from this geometry. This is traveled at the same time t that I recorded. So this is actually the separation between wavefronts, which is what we call wavelength. So the wavelength in this case, lambda, is going to be simply equal to, well, it's light, so it's traveling with the velocity c. So this one must have traveled ct to reach me. So it's going to be ct minus ut. So it's c minus u times t, where u is the velocity of the moving source in here. Okay, so this is how I'm measuring time. Okay, for me, this dispersion law still holds, namely c is equal to lambda times the frequency. So that's how I measure frequencies. As a matter of frequency that I measure, which is 1 over t, must be equal to c over lambda. So in other words, no, not 1 over t, I'm sorry. The frequency from this expression is c over lambda. And this is how I'm measuring lambda, this whole thing. So it's going to be c over c minus u times 1 over t. That is how I'm measuring this quantity in here, because that's lambda in the denominator. So I measure t, the time between two successive wavefronts, okay, two maximas if you wish. And I know because the wavefront is moving, I mean the source is moving with the velocity u, and the light is moving with the velocity c, and this is a dispersion law. This is true always. C is equal to lambda times frequency of the beam. So the way I'm measuring this frequency is going to be c over lambda, and this is true. However, I know from the relationship that we discussed a long time ago when we did here, when we did the time dilation, the time actually has shrunk. The t I measure is not the same t that the light actually has come up with. The light is actually emitting at the frequency t naught. And when I measure t, that is gamma times t naught. Okay. So because this is the proper time of light. This is how much time it has elapsed actually between two successive wavefronts. This is the one that I measure. This is the observer that is not moving. The factor gamma must be included in here. So if I do that, then the frequency I am measuring now is equal to c over c minus u times 1 over t. And 1 over t has this 1 over gamma times t naught. Remember, gamma is equal to 1 over square root of 1 minus u squared over c squared. Okay, so I have 1 over 1 gamma over this factor. So this becomes c over c minus u times the square root of 1 minus u squared over c squared divided by t naught, where t naught is the actual frequency of the beam. And t naught and the intrinsic frequency are related to f naught is equal to 1 over t naught. In other words, this is the actual frequency that is emitted. It's related to that ticking of the light, basically going back and forth. Okay, so f naught is related to that expression. I have some simplifications in here to do, and we're done. So f is going to be, oops, what happened to my notes in here? F is going to be equal to, am I still sharing my OneNotes? Yes, no? Everybody? What happened there?
Yeah.
Okay, because something happened to my screen. Okay, so let me rewrite it again before I make some simplification. So I have c times square root of 1 minus u squared over c squared divided by c minus u times the f naught. Okay, I'm going to bring this c inside the square root. That means I'm going to square it. So I'll have a c squared minus u squared divided by c squared times c squared. So I'll have c squared minus u squared. That's all. So I'm going to have a c squared minus u squared divided by c minus u, okay, times f naught, by the way, still have that. Okay, there is a simple algebra. The difference a squared minus b squared is a minus b times a plus b. So that's going to be equal to square root of c minus u times c plus u divided by, this is, I'm going to write it as square root of c minus u times c minus u. C minus u squared under the square root is the same. The only reason why I'm doing this so that I cancel these two terms times f naught. So it's going to be square root of c plus u divided by c minus u times f naught. In most practical applications, this u, even for the fast moving stars, is still small compared to c. So we're going to take the Taylor expansion and just keep the leading terms in both the numerator and the denominator. So this will become c plus 1/2 of u over c minus 1/2 of u times f naught. This is in the limit when u is very small compared to c. So this becomes equal to, take the c as a common factor, so it's 1 plus u over 2c. And this will become c divided by 1 minus u over 2c times f naught. So this is approximate, not exact, okay? So this is the exact expression. So if you have a super fast moving stuff, you have to use this expression, okay? If not, you can use the approximate one. So this is using just the leading Taylor series terms. So again, the c cancels the c, and 1 over minus epsilon is going to be 1 plus epsilon. So this is going to be 1 plus over 2uc times 1 plus, the negative becomes plus when I take it to the numerator. So it's going to be 1 over 2uc. And again, the leading terms in f naught is going to be simply equal to 1 times 1, that's 1. The leading term is this term times 1, and the other one terms times 1. So we'll have u over 2c plus u over 2c, which is just u over c. And the quadratic term is going to be neglected, plus any terms negligible in front of u squared over c squared, because I neglected this in here, in this term, so I cannot keep it now, okay, times f naught. The change in frequency, if you wish, delta f, which is f minus f naught, is going to be equal to u over c times f naught, and the relative shift in frequency f naught is equal to u over c. Okay, this is the shift in frequency when you have galaxies toward the end of the universe moving super, super fast. They move with speeds that are almost the speed of light. Okay, this is because of the expansion of the universe. This quantity will be shifted so much. So instead of, for example, the hydrogen atom having special frequencies, for example, in whatever color it is, in here, it's going to be shifted towards the red, very far away. This is the shift in frequency divided by the frequency that you're measuring for the light. That gives you how fast the galaxy is moving. This is how what's his name? I forgot his name now. Hubble discovered the expansion of the universe. When he did measurements on the faraway galaxies, he found that they are shifted, and from there they are shifted toward the red shifted. All frequencies are red shifted, so meaning that they are moving away from us. And from there, he was able to find how fast they are moving. Some of them are actually moving with very close from the speed of light, but this expression is not true anymore. You have to go back to this one to find it, okay? You have to go back to the original one. As a matter of fact, because the universe, I mean, space-time is not a particle, it can travel faster than the speed of light. That's the only thing that can travel faster than the speed of light, and that is space itself, okay? So there are portions of the universe that will fall below horizon for us, and this is, again, because of this expression in here. So for practical applications on a day-to-day business, this is a good expression to use. If not, then you have to go back into this expression. What this is it's the relative shift. Okay? Because you're dividing the difference in shift divided by f naught. Okay? So this is the Doppler effect from this point in here. Okay, we still have one item in here that we need to discuss, and that is item 4. I think we still have more, okay? Doppler effect in relativistic speeds. relativistic speeds. So this is item 4 of discussion. So far, so good. You guys remember the Doppler effect from your physics 2 class? This expression in here, where is it? This one? Basically, it's this one. Yes, no, maybe? Does this ring a bell something?
Yeah, it looks familiar.
I'm sorry?
Yeah, it does.
Yeah, okay. So, okay. So we have that. That's item 4 of the discussion. Addition of velocities. Another topic in here of velocities. And this has to do immediately with the experiment that we started with, the Michelson and Morley experiment. Okay, let's go back into the experiment. Doesn't matter which we're going to do. So we have x is equal to gamma times x prime plus ut prime. And t is equal to gamma times x, no, I'm sorry, times t prime plus u over c squared times x prime. Okay, sounds good. I'm going to have the differential form. I'm going to change, in other words, x1 and x2 separated by distance delta x and so on and so forth. The same thing is happening, by the way, for the primes, okay, where they're separated by delta x prime, measured in t1 and t2, so that this is delta t, which is a difference in times. These are measured in t1 primes and t2 primes, so that the separation in time is d delta prime. So if I do all of these differences, calculate x2 using x2 prime and t2 prime and t2 in here and t2 prime and so on and so forth, and do the one with the ones and so all of that. So we can find the differences at the end of the day, which is gamma times delta x prime plus u delta t prime. And delta t is going to be gamma times delta t prime plus u over c squared delta x prime. You guys understand what I'm saying in here? So that you just take the variations and at the end you end up with this expression. Make sense? Or do you want me to go in depth about this thing in here too? Make sense? Yes, guys, no, maybe? Okay, very good. Thank you, Isabel. So what I'm going to do is take the ratio of the two expressions. So delta x over delta t is, the gammas cancel when I take the ratios, okay? So I'm dividing this by that. So the gammas cancel, and I would be left with delta x prime plus u delta t prime over delta t prime plus u over c squared delta x prime. In the second terms in here, in the second side of this equation, I'm going to divide delta t prime. I'm going to divide delta t prime by both sides. In other words, I multiply by the same factor, 1 over delta t prime, the numerator and the denominator. So the fraction doesn't change. So what I will end up with is delta x over delta t is equal to delta x prime over delta t prime, plus the delta t prime cancels in here, so I'll be left with u, over delta t prime will cancel in here, so I'll be left with 1, and it will have 1 plus over c squared times delta x prime over delta t prime. Okay, I'm going to call, in the limit that delta t goes to 0, I'm going to call delta x over delta t, limit of this expression when delta t goes to 0, as v. And the limit that also delta t prime goes to 0, in other words, I'm taking back into the derivatives in here, this is v prime, okay? This stuff you have learned it from your first probably day of calculus. So the velocity, the way it's measured from this frame, is going to be equal to the velocity in the prime frame plus u over the 1 plus u over c squared times v prime. So imagine this. that you have two observers measuring two objects, the same object moving with respect to both of them. So here is object a reference frame O prime. This is O, and this is X. This is entire axis is X, and this is T prime, arms is T, and this is T prime. And you have an object in here that is moving. This observer will append the velocity V for it. This observer will append the velocity V prime for it. Okay, they are not necessarily the same value in here. Okay, but this frame is moving with the velocity U. This frame itself, O prime, is moving with the velocity U, and in it, an object is moving with the velocity V prime. The observer O measures the combined velocity of this U and V as being, or U and V prime as being this expression in here. Let's assume that this object is light, actually, a laser beam. That's experiment of Michelson and Morley. They have a laser beam actually moving with C. So in that case, V prime is equal to C. So he shines a light in here and it's moving on Earth, for example. And Earth is moving with 30 kilometers per second with respect to the sun. So the way we measure the velocity V is we say, okay, V prime is C. So we're going to put C in here. So it's going to be C plus U, that is how Earth is moving, divided by 1 plus, again, U over C squared. U is 30, C squared. And this is light. This is C. V prime is C. That's a laser beam. Obviously, the C and the C squared canceled. And I will end up with my measurements being C plus U over 1 plus U over C. And that's it, because I canceled one of the C squared with the C. So I'm left with the common denominator in the denominator is C. So I'm going to be left with C plus U over the common denominator is C, and the numerator of the denominator will be C plus U. Obviously, C plus U and C plus U will cancel. And the way I measure the velocity V is going to be, again, C will all the way go up and it's going to give me C. In other words, I will be left with a 1 over C, which is C. So if you shine a laser beam going with the velocity V prime equals to C, I measure also C. It's not that I will measure C plus, because in classical mechanics, what happened in here, if you shine a laser beam with a velocity C and the reference frame, the train basically going 50 miles per hour or 30 kilometers per second, it doesn't matter, then from the observer outside, he will see that light is moving with C and this frame is moving with V, with the U. So he will say, oh, that's moving with C plus V. That is how fast light is moving. But that's not true now. When we apply this formula that we derived from the Lorentz transformations for the velocity, which is this one, by the way, which is important for your homework assignments and exams and so on and so forth. When we apply that one and sub V prime with C, we will find that V is simply equal to C. It doesn't matter. No matter what you do, when you do it, you're going to always find C. And that's exactly what Michelson and Morley have found. That no matter where they turn their device and they shine the laser beam one way or the other, they will always find C. So you can never find velocity more than C for the laser beam that they were shining. Does this make sense to you guys? Yes, no? Yes, no, maybe. So what I did was I took the same Lorentz transformations and I placed the delta to them, and I took the ratios. The reason why I didn't do the D's, I know probably the textbooks said the D's, is because that's a no-no in calculus. You really have to take the deltas and then take the limit as the deltas go to 0, and then you will end up with the velocities. So this expression is true all the time, okay? And the limit when delta t's go to 0, that gives you a V prime, that gives you a V prime, and that gives you a V. So the velocity V is equal to V prime plus U over 1 plus u over c squared times v prime. And now when you subplot v prime equals to c, you're going to find the c again in here. Does this expression make sense to you guys? Yes, no, maybe? You guys think? Should I explain it again, or everything is good? Okay, very good. Thank you, Isabel. Hopefully everybody is, I know that the focus now, you guys are probably in exam time. I know we still have 1 minute before the class is over. So what I'm going to do is we're going to leave the dynamics to later on, to next Tuesday when we meet. And that's a big important topic because we're going to relate the energy to the mass and the momentum. And we're going to derive that expression. We'll find the kinetic energy, we'll find the work, and we'll find all of the things that we will need, including, since we're delaying it to then, including the how the momentum is related to the force, how to solve problems with that. That's actually should be true all the time. That's why we need to really express things in terms of momentum. And also, maybe if we have fun, I know you guys like Python, so probably I will bring a Python example in here using the Euler-Kromer method. And maybe we can do some fun in there, trying to find that indeed the velocity is maxed at c in this case, okay? No matter how much force you're going to apply to an object that is moving, even if you apply a billion newtons to it, the maximum you're going to get is a c in here, okay? Okay, sorry for what happened today with the cameras. Hopefully I will fix that problem. And I'm going to stop the recording. And the exam again is going to be available on Thursday at 8 o'clock in the morning, and will end at 1 p.m. Any questions before I stop the recording? No? Okay, I'll see you guys then.